Hello, everybody, and welcome to the presentation of my paper called Caption-Driven Explainability, Probing Convolutional Neural Networks for Bias via CLIP. My name is Patrick Koller, and I've got the pleasure to present this paper to you at the ICIP 2025. I also want to thank my mentor Amel Dravid and my advisors Guido Schuster and Agalos Katsaglos for this opportunity. First of all, I want to introduce you to the notation of a concept of a picture. If you look at this picture, what do you see? Most people would answer, I see a parrot. But if you take a closer look at this image, you see that it's actually the beautiful artwork of a body paint artist, which made the body paint and the position of the person look like a parrot. And now we can think about this original image and ask the question, what is the semantic meaning of this image? Should it be classified as a parrot, or should it be classified as a body painted person? I want you to have this question in mind during my presentation. Next, I want to motivate the concept for and the need for explainable AI methods, because our method is basically a new explainable AI method. So for example, if you have to build a binary classifier, an image classifier, with the two labels wolf or husky, and you see these six images with the prediction and the true ground truth label matching 5 out of 6 times, you will assume it's a pretty good classifier. On the other hand, if you apply any salient map producing method, for example, GradCam, and you would end up with the image on the right-hand side, you can see that your classifier was not focusing on the animal itself, which should be a husky or a wolf, but it was actually focusing on the background, as you can see on the right-hand side, where the classifier sees snow. So in this case, the classifier, every time it detected snow in the background, it classified the image as a husky, and every time there was no snow in the background, classified the image as a wolf. So basically, the developer was expecting to build a husky versus wolf classifier, but actually built a snow versus no snow classifier. And this could be problematic, and we would like to detect that. And our method actually helps to do this in a very natural way. So now I want to talk a little bit about the theory for bias. So for example, if you have a set of samples depicted in blue in here, and there are our training samples, we use those training samples to train our machine learning model. So the trained machine learning model has a learned function depicted in the green line in here. And if the training samples represent the distribution of our data or the shape of our true function depicted in red, very nicely, our model is able to learn that function. However, in this case, you can see the test samples, so the black crosses, they're basically not well represented by the training samples. And so there was a covariance shift, which means the training samples do not represent the function uniformly over all regions, and therefore this classifier will have a pretty good score for the training performance, but a pretty bad score for the test scenario. So, which example are we choosing to demonstrate our method? We chose a really simple, a trivial example, which is a subset of the MNIST dataset, which means handwritten digits. Actually, we build a binary classifier, which is able to distinguish between the number 5 and the number 8. So we have these digits. We feed them into a convolutional neural network, and we try to predict if the handwritten digit is a number 5 or if it is a number 8. The next thing that then we need to introduce before we can explain our own method is OpenAI's contrastive language image pre-training model, short CLIP. So basically what CLIP is doing, it is aligning an embedding space between images and texts. So give it an image and a set of captions. Clip is able to describe which caption describes the image the best. So just to explain really quick how it works, as soon as you have the trained clip model, which consists of an image encoder and of a text encoder, you take an image, in this case, it's a dog on the bottom left side, you feed it through the image encoder, through the clip image encoder, and you get a high-dimensional image embedding, I1. On the top-hand side, you create the text. It could be a template, as in this example, a photo of a object, which is a placeholder for one of the labels on the top left-hand side. And you take the sentence, put it through the text encoder, and for each sentence, you'll end up with a high-dimensional text embedding. Basically, you compute the dot product of the image embedding and the text embedding, and you end up with a cosine similarity. And you look for the highest cosine similarity, which is highlighted in light blue, so I1 and T3, which means text number 3 is the best description for image number 1. In this case, a photo of a dog is the best description for the picture on the bottom left. Now I want to talk really quickly about the data set we're using. So the data set we're using is we have a full data set of MNIST handwritten digits consisting of the numbers 5 and 8. And all the 5s are always red and all the 8s are always green. We do this because we want to introduce a bias into our training data set, such that our machine learning model will learn that bias, so we end up with a biased machine learning model in order to demonstrate how powerful our new method is, and that it will be able to detect this bias using captions in natural language. So now that we have a biased data set, we need to have a bias model. So our standalone model is the model which will be trained on the training data set. As you can see here, classic approach, we use the data set, we build a convolutional neural network classifier, and it works. So the output is, it's a number 5. But the question is why? Because if you look at the right-hand side, the performance, you can see the score, the accuracy, converges towards 100% for the training, the validation, and the test data set, which basically represents a low bias, low variance model and should be perfect in theory. Now, this is our method. Our method basically is really close or is building on top of OpenAI's CLIP model. As you can see, the top half of the image is actually the CLIP model. We have CLIP's image encoder in green, and we have CLIP's text encoder in purple. What we do, we come with a model to be explained. We call it the standalone image encoder, represented in red. And using our network surgery process, we integrate the information from our standalone image encoder to be explained into the CLIP image encoder. Now one could raise the question, like, don't we destroy the CLIP concept space, which CLIP already learned? And there's actually, it's a balancing act, right? Because on the left-hand side, shown on this picture, we want to incorporate as much information as possible from our standalone image encoder into the CLIP image encoder in order to get the best explanation possible. On the right-hand side of the picture, we don't want to incorporate too much information in order to screw up the already learned CLIP embedding similarities of the concept space. So it's a delicate balancing act. How does this network surgery process actually work? That's the big question. And in here, you can see how it works. So basically, we feed in a couple of images, and then we have the CLIP image encoder on top and the standalone image encoder on the bottom. So basically what you're doing, for each of the 4 last stages of the clip image encoder, we search the nearest neighbor, the one with the highest correlation of the standalone image encoder. And as soon as we found it, we take this activation map from the standalone image encoder and put it into the clip image encoder. And since we kind of integrate information from our standalone image encoder into the clip image encoder, we call this process the network surgery process. So what is the result of all this? So the result is, as you can see, it looks again like the structure, the architecture looks like a clip model, but the clip image encoder, which was green before, is now green and red because it's still the original clip image encoder, but certain activation maps has been replaced by the standalone image encoder to be explained. So the network surgery process was successful. And now we have incorporated some knowledge about the model to be explained into the clip image encoder. And now we need to come up with a set of captions. That's the normal procedure if you use clip. On the top left-hand side, you need to feed some possible captions into the text encoder. In this case, what are possible explanations for the classifier? It could be a photo of a digit with a value of 5, so depending on the values, which basically describe the shape of the image or the handwritten digit. Or there could be a color bias, so we could say if there's a photo of a red digit or a photo of a green digit. And so we have 2 captions describing the shape and 2 captions describing the color. And now we want to figure out which one is more important. I want to guide your eyes on the right-hand plot, actually, because if you look at the dominant concept of the standalone model, we can see that the distribution on the color feature is much larger than the value for the shape feature. So therefore, we successfully identified a color bias in our standalone model, therefore a color bias in our training data set. And this actually is the proof that probing convolutional neural networks for bias via Eclipse is actually working. Of course, somebody could raise the question, could we compare our approach to GradCam, gradient class activation maps? And yes, we can. And we actually have one advantage over it. And I want to demonstrate it to you. So if you take this picture of a green number 8, and you look at the heat maps produced by the gradient class activation maps, it will highlight a pixel space which contributed the most to the classification of the actual image. And obviously, if we have a binary classifier, which wants to distinguish between the digit number 5 and the digit number 8, the biggest difference in quotes is a gap in the digit on the lower left corner and the gap in the digit in the upper right corner, because this is mainly what's the difference between the number 5 and the number 8. But GradCam doesn't tell you if it's because of the shape or if it's because of the color. So you don't get the information, you just get a location. And now if you think again about the first image you've seen during the presentation, is it a parrot or is it a person with body paint? The same exact pixel space would be highlighted. But using GradCam, you would get the same exact pixel space. But using our method, you could ask, do you see, like designing the captions right, do you see a person with body paint on it, or do you see a parrot? So you can ask questions in natural language in order to understand what your standalone model is doing. So on the left-hand side, we see where we started. So without our explainable AI method, we built a classifier and it might be right. So it might classify a digit number 5 as a 5, but maybe because of a correlating color bias, not because of the shape. But using our method, we are able to figure out if there's a bias. And if there is a bias, we can move our eyes to the middle section of the image, and you can come up with a solution. In this case, it's a very simple solution. We can just remove the bias by using a grayscale transformation of all the images and retrain the model. And now we know we have an unbiased model because it's not biased by the color, because it's just using grayscale images now. So all the classifications are based on the shape of the digit. And this is actually what we want to do. So the advantages for our approach are basically concept level explanations. Instead of highlighting where an image, where in the image a model is looking, as saliency maps do, this method explains what the model is actually focusing on. Second, effective against covariate shift. So it demonstrates robustness where spurious and salient features occupy the same exact pixel space. Last but not least, our approach improves the trust. It empowers researchers to validate and improve model robustness before deployment, especially in critical and safety-sensitive domains. There are also two disadvantages that I'd like to mention. So it's a rather complex implementation, which means the network search tree process of selecting, matching, and swapping activation maps is non-trivial and computationally expensive. And last but not least, the dependence on CLIP's limitation, which means the method inherits CLIP's biases and limitations such as language bias in the captions or poor performance on narrow or domain-specific tasks. So before using our method, one should consult the original CLIP paper and see if CLIP performed well on these kind of tasks that you want to have explained. I hope you liked the presentation about our paper and I was able to motivate you to get in touch with me. I'm presenting this paper at the IEEE conference in September. If you're there, please get in touch with me. If you're not able to make it to ICIP 2025, please try to get in touch on our webpage. You can find it in the title here, patch0816.github.io. And you can find my email address there, my LinkedIn, or any other possibility to get in touch with me. I hope you liked the presentation, and I wish you a nice day. Bye.